Hello, Assalamualaikum. Good morning, all. How are you? Can you hear my voice?
Salam Doktor. Mana Doktor?
Hai, Assalamualaikum. Selamat Hari Raya.
Mak
Semua kat
Raya.
rumah ke? Semua kat rumah ke ni?
Saya kat rumah Doktor.
Ada yang kat kolej tak? Okay, so today we will talk about the elasticity and plasticity. So, have you watched the YouTube video that I share with you on Monday? Dah tengok ke YouTube video that I share on Monday? About what is that video is all about? About stress, strain, and compression, right? Okay, you all dah tengok ke YouTube video yang I share hari Isnin tu?
Dah Doktor.
Ada yang belum tengok tak? Ada yang belum tengok? Semua dah tengok Okay, so today we will talk about the theory of plasticity. Okay, before we proceed, I will explain some history. Okay, so the classical theory of plasticity grew out of the study method of metals in the late 19th. So it concerned materials which initially deform elastically, but initially deform elastically, but will deform plastically when it reach yield stress. So in metals and other crystals, the occurrence of plastic deformation at the micro scale level is due to the movement, the motion of dislocation, right? We will learn more about the dislocation in next chapter, and also migration of grain boundaries on the micro level. Okay. Okay, so anyone can explain to me what does it mean by stress, strain? Okay, in the YouTube video that I share with you, I have explained the meaning of this term. Right. So anyone can explain to me what does it mean by stress and what does it mean by strain? Anyone? Okay, tak ada volunteer. Ada tak yang boleh explain apa maksud stress, apa maksud strain? Before we proceed on plasticity. Okay, I will ask again this question later. Okay, let me proceed first. Okay, so we will discuss about the elasticity and plasticity today. So a degree of which a structure deform or strain depend on the magnitude of imposed stress, right? So stress and strain are proportional to each other. Okay, stress and strain are proportional to each other, and we have this equation that we call as a Hooke's law. Okay, this is the equation of a Hooke's law. Okay, this is sigma. This symbol is sigma equals to E times epsilon. Okay, what is sigma? What is this? What is sigma? Okay, sigma, the symbol sigma is stress, and epsilon is, what is this? Okay, epsilon is symbol of epsilon. Siapa tahu what is this symbol represent? Epsilon.
Strain.
Ya, betul. Okay, this is a Hooke's law. Stress equals to E is Young modulus. Okay, E yang besar ni, this is Young modulus times epsilon. Epsilon is strain. Okay. Okay, if you look at the figure here, okay, this is what we call as a stress and strain diagram. Okay, so we can see here that the linear relation in elastic region, so this is an elastic region, is defined by Hooke's law. Okay, Hooke's law, stress equals to Young modulus epsilon or strain. Okay, so the ratio between the stress and strain is what we call as a Young modulus. And Hooke's law, it usually only applies for small strain. Okay, Hooke's law only applies for small strain. But what happened? Can you guess what happened if we have a larger strain? Okay, what happened if we have a larger strain? When we have a larger strain, the relationship between the stress and strain is no longer linear. So if you take a look at the figure here, at this stress and strain diagram, at a small strain, we have a linear relationship between stress and strain. So within this region, we have Hooke's law that we can apply. But when we enter this region here, we have a larger strain. So here we can see that the relationship between stress and strain is no longer linear. So Hooke's law in this region is not longer applicable. So a deformation are not reversed when we reach this stage, even when we remove the loading. Faham Okay. Bila kita dah sampai, when we have reached this region, kita sampai dekat this region, even we remove the loading, for example, we have when we reach this region, even when we remove the loading, the spring will not going back to its original position. Okay, a deformation in which a stress and strain are proportional is what we call an elastic deformation, like what we can see here. Here we have elastic deformation, right? Elastic deformation, it is non-permanent, meaning that, like what I have mentioned before, when we release the loading, the piece will return to its original shape. Okay. Okay, note that when I mention about a plastic, do I refer to plastic like what we have in polymeric material? When I mention plastic here, can you associate this with a plastic bag? Boleh tak? Okay. Okay, when I mention about plastic here, it does not refer to a plastic like what we have in polymeric material, or for example, plastic bag. But when I mention this term plastic, it means that permanent strain in any material. Okay, so here we have the definition of plasticity. So plasticity, we can define it as an ability of material to undergo some degree of permanent deformation without a rupture. So plastic deformation occurred after elastic limit has been exceeded. Okay, like what we can see in this graph here. This is a force versus deformation, right? And plasticity will also increase with the increase in temperature, right? Okay. Okay, it has been assumed that that elastic deformation is independent. Okay, elastic deformation is time independent. Applied stress will produce instantaneous elastic strain that remain constant over time. When we release the loading, the strain will immediately returns to zero. For example, here we have this graph. When we apply loading, the strain will increase, and the relationship between stress and strain is proportional. But when we reduce the loading, we remove the loading, then immediately the strain will return to zero. However, for unelastic material, the elastic deformation will continue even after the stress application. Okay, so we can define unelasticity. Okay, we can define unelasticity as a time-dependent elastic behavior. Okay, so in metal, this phenomenon is quite less compared to in polymer, but in polymer, we don't really call it as an elasticity behavior. In polymer, we use this term, viscoelastic behavior. Okay, have you ever heard about the term viscoelastic? Pernah dengar tak this term, viscoelastic? Anyone? Anyone pernah dengar this term viscoelastic? Okay, viscoelasticity is a materials that exhibit both viscous and elastic characteristic when experience deformation. Okay, exhibit both viscous and elastic. Okay, we see the word here is a combination of viscosity and elasticity. So this is a material that exhibit both viscous and elastic deformation. Okay, I have mentioned just now the term viscoelastic. Usually we associate with a polymeric material. For metal, usually we call it unelasticity. Okay. Okay, here are some examples of viscoelastic behavior. Okay, before that, viscous material is a strain material is when the strain develops over a period of time and after the stress is removed, it does not return to its original shape. Okay, and the development of a strain, it takes time and not proportional or not in phase with the applied stress, and the material will remain deformed even after we remove the applied stress or if after we remove the loading. Okay, take a look at the figure here. Okay, this is the stress cycle. Okay, stress versus time. A specimen is loaded to a given stress and subsequently unloaded. Okay, dekat specimen tu kita apply loading at a specific stress, and subsequently we remove the loading. Okay, for ideal elastic solid, like what we can see here, this is the strain response of ideal elastic solid. So we can see the elastic strain only constant with time. Okay, so the example of a material with this behavior is thermoplastic. Okay, thermoplastic below TG. What is TG? Tahu tak TG ni apa?
Glass transition.
Glass transition temperature. So example of a material that exhibit this strain response behavior is thermoplastic below glass transition temperature, thermoset, ceramic and plastic. But we also have a strain response like this one. Okay. Okay, some instantaneous elastic strain, like what we can see here, instantaneous elastic strain that followed by elastic strain that increase with time under stress, and it recovers slowly when we over time. Okay, and we can see in this material some plastic flow may also occur. So example of this material is thermoplastic at a temperature around a glass transition temperature. Okay, okay. So what is viscosity? What are viscosity and viscous material? Okay, can you give me what is the definition of viscosity? What is the definition of viscosity? Okay, for example, if we have a water and a honey, okay, air dengan madu, which one is more viscous?
Honey.
Honey is more viscous, right? Because it resists to flow compared to water that can flow freely compared to honey. Honey is more harder to flow. So we can say that honey is more viscous than water. So in a viscoelastic material that is held under constant strain, if we wait, we can see that the level of stress decrease over a period of time. Okay, you can see that the level of stress decrease over a period of time, and this phenomenon is what we call as a stress relaxation. Ataupun in Malay, kelonggaran bahan kot. Okay. Okay, the recovery of a strain, on the other hand, refers to the change in shape of the material after the stress that caused deformation is removed. Okay. Okay. Stress relaxation meaning that the stress relaxation mean that the stress decrease over a period of time. Okay, this is the definition of a stress relaxation. Okay, when we held that material, under constant strain. Okay, okay. When we held that material under a constant strain, we can see that the stress will decrease over a period of time, like this one. For example, this is what we call as a stress relaxation. And then we have this recovery of strain it refers to change in shape of the material. Change in shape of the material after the stress that caused a deformation is removed. After the stress that caused deformation is removed. Stress is removed. Okay, some example of a viscoelastic material. Okay, for example, we have a synthetic polymers, wood, and also human tissue, as well as metal at a high temperature. All these material, it display significant viscoelastic effect. Okay, now we talk a bit about Newtonian and non-Newtonian material. Okay, Newtonian fluid, non-Newtonian fluid, rheopectic, thixotropic dilatant. What are the differences between all these liquid properties? Okay, all these are liquid properties. Newtonian fluid, non-Newtonian fluid, rheopectic, thixotropic dilatant. All these are properties of a liquid or fluid. Okay. Okay, what are the differences between all these terms? And the most important is why does all these properties matter? Okay. Okay, all fluid can be broken into two basic types. So we have Newtonian fluid and non-Newtonian fluid. Okay, Newtonian fluid is a fluid viscosity that remain constant no matter the amount of shear that applied for constant temperature. So this fluid have a linear relationship between viscosity and shear stress. And then we have a non-linear fluid. Okay, as you can guess, this non-Newtonian fluid are the opposite of a Newtonian fluid. Okay, when shear is applied to a non-Newtonian fluid, the viscosity of the fluid changes, and the behavior of the fluid can be described in one of the four ways. Okay, we have a dilatant. Okay, this is a for non-Newtonian fluid. Okay, we have a dilatant, we have a pseudoplastic, and we have a rheopectic and a thixotropic. Okay, okay, what I have mentioned just now, when shear is applied to non-Newtonian fluid, viscosity of the fluid changes. Okay, when we apply shear, viscosity for non-Newtonian fluid will changes. And these changes can be described in this four ways. We have dilatant, pseudoplastic, rheopectic, and thixotropic. Okay, dilatant. For dilatant, meaning that the viscosity of the fluid will increase. Okay, like what we can see here, the viscosity of the fluid increase when stress or shear is applied. Okay, and then we have a pseudoplastic. Okay, we have a pseudoplastic is the opposite of a dilatant. The more we apply shear or stress, the less viscous it becomes. Okay, so this chart here shows how viscosity changes in respect to the amount of shear or the stress applied to the fluid. And then here we have a rheopectic and a thixotropic. Okay, we can see here for rheopectic liquid, it is quite similar to dilatant, except here we involve time. Okay, so rheopectic is very similar to dilatant. That when we apply shear or stress, viscosity increase. But the difference here, we include time. Over time, the viscosity will increase. All right. And then we have a thixotropic. The fluid with thixotropic properties will decrease in viscosity when shear is applied. Okay. This is a time dependent property as well. Okay. Okay. Can you give example? Example of thixotropic fluid that you can think of, where the viscosity will decrease over time. Ada idea tak?
Mayonnaise.
Mayonnaise, maybe. Mayonnaise lama-lama dia cair ke? Over time, viscosity dia.
Butter.
Butter.
Yeah.
Tapi kalau butter, kalau kita panaskan kan, betul tak? Okay, maybe certain type of pan kot kan, macam cat kan. Ada ke cat yang cair bila kita tinggalkan dia?
Itu dia mendap kan?
Dia mendap Maybe pan is a good example of a thixotropic material. Oh, actually bukan cair sebab viscosity ni can flow freely, right? Betul tak? What is the definition of viscosity? Tadi saya dah mention. Apa maksud? Apa definition
Dia resist
of
untuk flow.
resist flow? So kalau dia turun ni, maksudnya dia makin pekat atau makin cair?
Kalau turun makin pekat lah.
Makin pekat lah kan, sebab dia thick kan.
Viscosity low.
Viscosity dia menurun. So paint is a good example lah. Bila kita kacau-kacau dia kan, over time, lama-lama dia makin pekat ataupun gam.
Makin cair kan? Pening lah. Makin cair. Low viscosity macam water lah.
Saya rasa dia makin pekat.
Pekat.
Okay, tak apa, nanti you check Okay, untuk jangan pening. Untuk thixotropic, biopectic, dilatant and pseudoplastic. Okay, nanti you all check dia sama dia makin pekat atau dia makin cair when the viscosity decrease stress over time. Okay, this is the example of a viscoelastic material. Okay, what is this? Ini apa ni? Di racket tennis So the common example of a stress relaxation. Okay, stress relaxation. Okay, kalau you ada racket ni kan lama-lama dia macam makin longgar kan, walaupun kita tak main. Okay. Okay, this is the example of a stress relaxation. Okay.
Getar tu. Rubber band.
Rubber band.
Tapi keras.
Okay, we can see that the level of stress nylon string dekat tennis racket ataupun badminton punya racket, walaupun kita tak pakai racket tu, it will decrease with time. Lama-lama dia punya string ni makin terlonggar kan. Kita kena ketatkan balik. So that is the example of a stress relaxation. Lama-lama dia punya stress tu dia makin turun. Okay. So unlike a viscous material, when applied stress is removed, part of the strain will recover over a period of time. Okay, so this is a good example of stress relaxation in a nylon string in racket. Okay, just to recap, elastic deformation is reversible, like what we can see here. Okay, you bayangkan ni adalah atom. Okay, when we apply loading, dia macam ada spring between the atom. Okay, this is bonding. The bonding will stretch, but when we unload, it will return to initial. Okay, so elastic deformation meaning that the material will return to its original position when the force is removed. We have two types of elastic behavior, the linear elastic and non-linear elastic. Okay, for plastic deformation, we can see here the plastic deformation meaning a permanent deformation. Okay. Okay. So this is the initial stage when we apply loading, the bond with the original atom neighbors start to break. Okay, dia punya bond tu, okay, dia akan break. Okay, the bond will break and we will reform a new group of atom. So okay, so when this occur, the stress is relieved. The material will no longer return to its original form. The deformation is permanent and non-recoverable. Okay, so we can say that the material now move into the region that we call as a plastic deformation. Okay, for most metallic material, the elastic deformation is quite small. Okay, at some point, the strain is no longer proportional to the applied stress. Okay, untuk metallic material, for metallic material, elastic deformation is relatively small compared to polymeric material. Okay, if you take a look at this picture here, which one is plastic and which one is elastic deformation, A or B? How about A? Is this plastic deformation or elastic deformation? Mana satu plastic deformation, mana satu elastic deformation?
A plastic.
A is a plastic deformation and B is elastic deformation, but this one is non-linear. Example of this type of material is rubber. Okay, we can see for this type of material, even it is still elastic deformation, it does not follow Hooke's law, right? Dia tak ikut Hooke's law, It does not follow Hooke's law. Because we cannot see a straight line that proportional relationship between the force and the extension. But still we call this one as an elastic deformation. Okay, we can see that it does not follow the same path backward, right? When we apply loading, so this is the path, but when we remove the loading, it does not follow the same path backward. Okay, what does it mean? Apa maksud ini? Meaning that when we apply loading, more work is needed to stretch the rubber. Kita perlukan banyak tenaga untuk tarik rubber tu, compared to the work that we need to put it back into its original position. Okay, so energy yang area dekat bawah graf ni, so untuk loading required more work compared to unloading. So where does all the excess energy go? Okay, the excess energy released as heat. Okay, the work for loading, the work that we required for loading is more than unloading. Okay, tenaga yang kita perlukan untuk tarik rubber band tu lagi banyak daripada tenaga yang diperlukan untuk letak dia balik kepada original position. And the excess energy between the differences between loading and unloading, it will be released as a heat. Okay, kalau you tarik rubber band tu kan lama-lama dia panas kan, betul tak? So that is where the excess energy go. It is released as a hit. Okay, here some assumption of plasticity. When we formulating a basic plasticity theory, here some assumption. The plastic flow, we assume it occurs at a constant volume. And the modest hydrostatic pressure, it do not cause yielding. P less than E divided by 100. And when we say modest, we mean that the pressure here is less than the modulus over 100. And we also neglect the strain hardening. We assume that we have perfect plasticity, and we also assume the material is isotopic. It have identical values of property in all direction. Okay, some materials, it does not exhibit a linear stress strain curve within elastic region, like what I have shown in previous slide. Some materials do not exhibit linearity within elastic region. So it is not possible to determine the modulus easily. So example of this material, gray cast iron, concrete, and many types of polymer. So this for nonlinear material, we use the slope of tangent, a second modulus, then we have a tangent modulus here. So we use the slope of a tangent as a varying quantity to replace the Young modulus. Okay, this is the example problem. We have a piece of copper, originally 305 millimeter or 12 inches long. Pull intention with stress equal to 276 megapascal or 40,000 pounds square inch. Okay, if the deformation is entirely elastic, can you calculate the resultant elongation? We take the Young modulus for copper is 110 gigapascal. Okay, can you solve this question? Boleh buat tak? Okay, to solve this question, okay, we use a Hooke's law equation. So this is the Hooke's law equation. Stress equals to strain times the Young modulus E. So this strain is the change in length over original length times E. So we want to find this. So we need to solve for change in length because we want to calculate the resultant elongation. Kita solving for this change in length, we arrange the equation, so we have this equation. So the value of shear, the value of this sigma, the value of sigma is the stress. The value of stress sigma equals to 276 megapascal. And the original length is 305 millimeter. Panjang asal dia 305 mm. And the magnitude of Young modulus is 110 gigapascal. So we just plug in all this value into this equation. So the change in length is 276 megapascal. This is the applied stress, times original length divided by Young modulus. So we assume that deformation is entirely elastic. The resultant elongation is 0.77 mm. Faham? Boleh faham Boleh buat tak? Faham Okay, so any question? Any question?
Tak ada.
Tak ada.
Tak ada.